Hello, and welcome to the lecture on 5.4. Today we're going to talk about some more trigonometric graphs. Specifically, we're going to talk about tangent, cotangent, secant, and cosecant. Well, first, let's go ahead and recall f of x plus p equals f of x means that this function f of x is periodic. If this is true for every x value, this function is periodic. Now, we've previously found that sine and cosine were periodic, so we can actually assume that tangent and cotangent, secant and cosecant will also be periodic, and they are. They might have different periods, but they are periodic. Periodic properties. The functions tangent and cotangents have period pi. This means that tangent of x plus pi is equal to tangent for all x values. Similarly, cotangent of x plus pi is equal to cotangent of x for every single x value. The functions cosecant and secant have period 2 pi, and this means cosecant of x plus 2 pi is equal to cosecant of x for every x value, and similarly, secant of x plus 2 pi is equal to secant of x for every x value. Now we're going to look at this cosecant and secant in a little bit. Right now we're going to focus on tangent and cotangent. But we need to look at some properties that these two graphs are going to share. So let's recall what a vertical asymptote is really quickly. If y goes to infinity as x goes to a, or y goes to negative infinity as x goes to a, then we say that x equals a is a vertical asymptote. I want to recall two other things. Specifically here, tangent of x is equal to sine of x divided by cosine of x. And secant of x is equal to 1 divided by cosine of x. And similarly, cotangent of x is equal to cosine of x divided by sine of x. And cosecant of x is equal to 1 divided by sine of x. Now let's notice really quickly. I want to notice here that cotangent has sine x as a denominator, same as cosecant. Secant and tangent, on the other hand, have cosine as a denominator. Now these are where vertical asymptotes will occur. When you have a 0 in the denominator and a finite non-zero number in the numerator, then we get a vertical asymptote. It will mean that our y will be going to infinity as our x is approaching that value. So let me explain this very, very quickly and briefly. Suppose that we have x equals a right here. At this line, this vertical line here is x equals a. If as our x values get closer and closer to this x equals a, our y value is going to infinity, then we're going to have a vertical asymptote. That's what it means. So our y value will increase without bound while our x value is getting closer and closer to a specific value, namely that x equals a value. Let me show you a function with a vertical asymptote here with 1 over x. Notice that the numerator is always a finite non-zero number, 1, and the denominator can be many different numbers. But it can't be 0 because we can never divide by 0. And that reason is, if we get close to 0, say 0.1, this is actually pretty far from 0 still. We're 1/10 of a unit away from 1. If we multiply top and bottom by 10, then we end up with 10 divided by 1, which is just 10. Now, instead, what if we got even closer to 0? What if our x value got even closer to 0? What if we said it was 1/100th of a unit away from 0? We multiply top and bottom by 100, we get 100 divided by 1, which is 100. The y value would be 100, saying that y is equal to 1 over x. So if we were 1/10 of a unit away from 0, our y value is 10. If we're 1/100th of a unit away from 0, our y value is 100. If we're 1/1000th, then our y value becomes 1,000 because we can multiply top and bottom by 1,000, and we would end up with 1,000 divided by 1. So notice, as our x value gets closer and closer to 0, our y values are growing to a very large unbounded number. Specifically, they're going towards infinity. Now, this is what it means to have a vertical asymptote. If cosine is 0, that means the x value on the unit circle is 0. That would mean then that sine is 1, because remember, it has to be a radius of 1 on the unit circle. It has to fit the equation x squared plus y squared equals 1. And we can say a very similar thing here. If cosine is 0, then we get 1 divided by 0. So a non-zero finite number divided by 0. So we're going to get a vertical asymptote when cosine is 0 for these two. When sine is 0, we get a vertical asymptote for these two functions, cotangent of x and cosecant of x. Let me write this out as a note. For tangent and secant, any x value that makes cosine of x equal to 0, we get a vertical asymptote. As I stated before, if cosine is 0, we get 1 divided by 0. If cosine is 0, we get 1 divided by 0 for both tangent and secant. Similarly, for cotangent of x and cosecant of x, any x value that makes sine of x equal to 0 will be a vertical asymptote for the exact same reasons. If sine is 0, cosine is 1, so we would get 1 divided by 0. If sine is 0, we end up with 1 divided by 0. So we cannot divide by 0, and as we get closer and closer to the x values that make these denominators 0 for each respective function, our y value will grow without bound, meaning it'll go to infinity or it will go down to negative infinity, which means we have a vertical asymptote. So with that, let's go ahead and graph tangent and cotangent. So we have our axes. The first thing I want to do, I want to look at for what values tangent will have a vertical asymptote. If you remember, this is when cosine of x is equal to 0. So what values of x make cosine equal to 0? Well, if you recall, cosine of pi over 2 is 0, and cosine of negative pi over 2 is 0. So we'll have a vertical asymptote at x equals pi over 2 and x equals negative pi over 2. But are there any other ones? Remember, tangent is periodic, and it has period pi. So at every pi units, we're going to have a vertical asymptote. You can see that these two are pi units apart. If we subtract them, pi over 2 minus a negative pi over 2, we end up with a distance of pi. So let's go ahead and graph at pi over 2 and negative pi over 2 our vertical asymptotes. We have pi over 2 here, negative pi over 2 here. Let's graph these vertical asymptotes here. So we have vertical asymptotes here and here. Now, let's go ahead and graph some points so we know where to plot our tangent curve. We have x here, tangent of x is equal to y here. So our x value and our y value. If x is equal to negative pi over 3, then our y value ends up being negative square root 3, because it would be the same thing as sine of negative pi over 3 divided by cosine of negative pi over 3. You remember, negative pi over 3, sine is the larger value, but negative pi over 3 is in quadrant 4 because we move clockwise, not counterclockwise. So we end up with a negative root 3 over 2 for sine and a positive 1/2 for cosine. When we flip and multiply, we get negative root 3 over 2. At negative pi over 4, tangent will be negative 1, quadrant 4. Negative pi over 6, we would flip these two, and we get, and we would have negative 1 divided by root 3. At 0, we have 0 because sine is 0. We plug in 0 here, we have sine of 0 is 0. Cosine of 0 is 1. And then the positive versions of these values. So we would have at pi over 6, we would have positive 1 divided by root 3. At pi over 4, we have positive 1 for our y value, and at positive pi over 3, we would get the positive root 3 for our y value. If this is 1, let's go ahead and plot these. But our curve will look something like this. This should be a little bit more rounded. So this would be our tangent curve. Try a problem on the accompanying worksheet. Graph y equals cotangent x. And recall that cotangent of x is equal to cosine of x divided by sine of x. I would follow the exact same process that we just did. You should be able to get it on your own. Note that cotangent does not intersect the origin. Let's move on to the graphs of secant and cosecant now. So recall that tangent of x is equal to sine of x divided by cosine of x. And secant of x is 1 divided by cosine of x. So notice here that as x changes, the denominator is changing in secant. But as x changes for tangent, both the numerator and denominator are changing. So these graphs are a little bit different than tangent and cotangent. Actually, they're going to be very related to sine and cosine. Let's go ahead and go back through exactly how we did the, or let's start in the same way that we did with tangent. So first recall, secant of x is equal to 1 over cosine. What this means then is that whenever cosine is equal to 0, we have a vertical asymptote. Cosine is 0 at x equals pi over 2 and 3 pi over 2 for our first period of cosine and secant. What this then means is, if we tried to plug these values in for x here, cosine would give us a 0, and we would have 1 divided by 0, which is a vertical asymptote. So these two values are not in the domain of secant. They're in the domain of cosine, but they're not in the domain of secant. So what I'm going to do is I'm going to plot the cosine curve. And then I'm going to use that curve in order to sketch the graph of secant. So we already know at pi over 2, we have a vertical asymptote. All this pi, 3 pi over 2, also a vertical asymptote, and 2 pi here. So for plotting cosine, you have to remember that cosine starts at a maxima value, 1. It comes down, touches here at pi over 2, it touches the x-axis. We get a negative 1 at pi, 0 at 3 pi over 2, and then back up to 1 at 2 pi. We get this. And the curve looks something like this. This is the cosine curve, not the secant curve. But notice here, we have 0 values for cosine. And remember, when cosine is 0, we're going to have a vertical asymptote for secant. So let's go ahead and draw those. So we have our vertical asymptotes for secant now. Now, if we want to plot values, you can for secant. It's not too bad, but I'm just going to go ahead and draw the curve because it's actually really relatively easy. You want to follow your vertical asymptotes. So the secant curve will be plotted here at the max and min of cosine, and it'll follow the asymptotes. So we get something like this. And then here we go up and follow this asymptote, and we come down following this asymptote here. I do want to note that you have to remember that cosine goes on forever. So we can continue the cosine plot if we want to, and we would have another vertical asymptote here at 5 pi over 2, which would then mean that we would have to continue our secant curve following this asymptote as well. But we usually only graph one period of secant and cosecant, also sine and cosine and tangent, of course, in cotangent. So I'm not going to actually plot this part. I'm just going to leave it dotted for you, just as a reminder that these curves will repeat forever. Now go ahead and try one on the accompanying worksheet. graph y equals cosecant of x. And recall that cosecant of x is equal to 1 over sine of x. So follow the exact same steps that I did. Find your vertical asymptotes, plot them, and then sketch the sine curve instead of the cosine curve, and then plot cosecant instead. It'll look very similar to secant. All right, the next thing I want to talk about, the next topic that I want to cover is transforming tangent and cotangent. Let's recall how we shift a graph. If we're given the graph of y equals f of x, and we know that c is greater than 0, then following properties will shift our graphs in the following ways. The graph of f of x minus c shifts the graph y equals f of x to the right c units. The graph of y equals f of x plus c shifts the graph of y equals f of x to the left c units. The graph of y equals f of x plus c shifts the graph y equals f of x up c units. The graph of y equals f of x minus c shifts y equals f of x down c units. These are the 4 different shifts that we can do in a graph. Now let's go over stretching and compressing, and this time we're going to assume that a is greater than 1. The graph of y equals f of ax contracts the graph y equals f of x horizontally by a factor of a. The graph y equals f of 1 divided by a times x stretches the graph y equals f of x horizontally by a factor of a. The graph y equals a f of x stretches y equals f of x vertically by a factor of a. The graph y equals 1 divided by a times f of x contracts y equals f of x vertically by a factor of a. Then we have our reflections. The graph y equals negative f of x reflects the graph y equals f of x about the x-axis. The graph y equals f of negative x reflects the graph y equals f of x about the y-axis. So we've gone over these a couple of times before. If you want a deep dive of why these are the way they are, in the Precalculus Algebra videos, section 2.6, you'll find what you need. What we're going to do is we're going to use these transformations in order to transform the tangent graph. We're going to figure out how we can graph an arbitrary tangent with some different manipulations in the graph. Let's start by analyzing the graph y equals a tangent kx. We also are analyzing y equals a cotangent kx as well. But we're mostly just focusing on the tangent graph. Okay. So here's the graph of tangent. Remember that k is affecting the horizontal stretching and compressing. So if k is greater than 0, everything compresses towards the y-axis. If k is less than 0, everything stretches away from the y-axis. Now I want to focus for a second on when k is greater than 0 and see what happens, because I really want to know what the period of this function is when we have a k in front of the x. Now, from this point to this point is exactly 1 period. In this case, it's pi units because this is the graph of tangent of x with k equal to 1. Now, the x-coordinate here is going to move towards the y-axis by a factor of k. So, if k is greater than 0, then the x-coordinate of this point is going to move towards the y-axis by a factor of k. It's going to shrink. So we have to cut this x value by a factor of k. Let's suppose that k is equal to 2. Then the x-coordinate for this point would be cut in half. Here it's at pi, so the new x-coordinate would be here at pi over 2. So the new period of these graphs is going to be p equals I divided by k. Now, the exact same period formula works when k is less than 1 as well. If k is less than 1, we're stretching away from the y-axis, but dividing by something that's less than 1 actually increases the numerator. And that's why we get a stretch. Tangent and cotangent. Functions y equals a tangent kx and y equals a cotangent kx, where k is greater than 0, have period p equals pi divided by k. Now this is important when we actually go to graph these new functions, when we're graphing a shifted or a modified tangent and cotangent. Note here that this a, it's not an amplitude, because amplitude refers to sines and cosines, where it's the maximum value away from the axis over which the sine and cosine oscillate. For tangent and cotangent and secant and cosecant, a is actually called just the stretching factor. It's how much you're stretching vertically or compressing vertically. But it's usually not that important. Let's go ahead and do an example here where we graph a function that looks like this. We're going to graph y equals cotangent of 2x. All right. Now the first thing that I want to find is the period. How do we find the period? Well, the period is going to be p equals I divided by k. Our old period divided by this factor. And in our case, k is 2. So our new period is going to be pi over 2. This means that an entire cycle of cotangent will fit within an interval that has length pi over 2. So I want to go over this just a little bit more. Cotangent of x, the one that we're not graphing, the original cotangent, is usually graphed on 0 to pi. This is normally where we graph cotangent. Notice that the period is pi. Cotangent of 2x, on the other hand, will be graphed on 0 to pi over 2, where we have a period of pi over 2. So let's go ahead and draw that out. We have our pi over 2 and pi over 4. This is halfway across the cotangent curve. Now remember, cotangent of 2x is the same thing as cosine of 2x divided by sine of 2x. Because sine is equal to 0 when x is equal to 0, we get a vertical asymptote at 0, just like this. We're also going to have a vertical asymptote at pi over 2. So notice if sine is equal to 0, if the denominator is equal to 0, then this function has to have a vertical asymptote. So we end up with, if x is equal to 0, we have sine of 0, which is 0, which means we have a vertical asymptote at x equals 0. If x is equal to pi over 2, plugging in pi over 2 for x, we get 2 times pi over 2, which would be pi. So sine of pi is 0 as well. So we get a vertical asymptote here. And then if you remember how cotangent is graphed, it will look something like this. Go ahead and try one on the accompanying worksheet. Notice that your k is going to be less than 1 in this case, so you actually get a vertical, or you actually get a horizontal stretch, not a compress like we have here. This is a horizontal compress. This would be a horizontal stretch. So your period's going to be bigger than pi. All right, let's go ahead and add the horizontal shift now. Graph cotangent of 2x minus pi over 4. Notice that my 2 is factored out. That's important. Always make sure that you do that whenever you're graphing a function like this. Now, all I've done is added a horizontal shift to the previous graph. This graph right here is y equals cotangent of 2x. So what I've done is added in a horizontal shift, pi over 4. So we're going to shift this graph horizontally by pi over 4 units. Right, so every single point on the cotangent graph. Now, which way do we shift? Do we shift it to the left or do we shift it to the right? If you said to the right, then you're correct. We have a minus pi over 4, which means we shift to the right pi over 4 units. Again, I cannot emphasize this enough. 2 is factored out. Make sure whenever your k is not factored out and you have a horizontal shift, make sure to factor it out, because this is the horizontal shift. If you distribute the 2, you would have minus pi over 2. That is not the horizontal shift. So what we're going to do is we're going to take this and we're going to translate it to our new graph. All of our vertical asymptotes will shift by pi over 4 units as well. So we get one here at pi over 4, and we get one at 3 pi over 4. So this vertical asymptote shifted to the pi over 4. That's this one. This one shifted pi over 4 to the right, which becomes 3 pi over 4. But then all these points will just fall exactly how they were before. We end up with this graph here, just like this. Whenever you're asked to graph something like this, where you have a horizontal shift, generally you want to graph the period first, like this, before the horizontal shift, and then you want to add in the horizontal shift by just shifting this graph. So we graphed this one first, which was cotangent of 2x, and then we graph the horizontal shift of this graph. So we take every point on this graph and just shift it. That's usually the process to graphing these types of functions. All right, the next topic I want to talk about is transformations of secant and cosecant. Secant and cosecant are a little bit easier to transform than tangent and cotangent, because all we really need to do is transform the sine and cosine graph that we use as a guideline to graphing secant and cosecant. Recall? When graphing secant and cosecant, we first graph the cosine or sine graph as a guide. So when we transform secant and cosecant, we just transform the sine and the cosine graph. And then we can just sketch the graph of cosecant or secant by using the guide of sine and cosine. Now, if you remember, sine and cosine have a period of 2 pi. So it should make sense that cosecant and secant also have a period of 2 pi. The functions y equals a cosecant kx and y equals a secant cox have a period of 2 pi divided by k, just like the period of sine and cosine when we transform those graphs. That's exactly why it is that way, because secant and cosecant have an underlying sine and cosine graph. Do an example and graph y equals secant 2x. And recall that secant is 1 over cosine, so secant 2x is the same thing as 1 over cosine 2x. So we need to use the cosine graph as a guide. Our guide graph is y is equal to, let's do this in red, is y is equal to cosine 2x. I'm going to graph this graph in red. Now, in order to graph cosine of 2x, we need to figure out what the period is first. Here, the period is 2 pi divided by k. Our k is 2, which means that the period is going to be 2 pi divided by 2, or just pi. We go out pi units, pi over 2, pi over 4, 3 pi over 4. Okay, now what I want to do is just graph the cosine of 2x. If I had an amplitude, the y value would increase or decrease based on what the amplitude was. But we don't have an amplitude for this graph, so we just use 1, like we normally would. Cosine starts at a maximum, across here, go down -1, here, and then here. Cosine always has the same shape. When we graph cosine, really what we're adjusting are the x and the y values to fit our cosine. So this is my cosine graph. Now, we want to take note where the cosine hits the x-axis, because that means that we have a vertical asymptote for our secant graph. We draw our vertical asymptotes here, and here, where the cosine is equal to 0, i.e. where it's crossing the x-axis. Then we just sketch the graph of secant by following our guide. It is the cosine graph and our vertical asymptotes. And of course, remember that cosine goes on forever, thus the secant graph also goes on forever. All right, go ahead and try one on the accompanying worksheet. Graph cosecant 1/2 x. That's going to be it for today's lecture. I'll see you all in the next one.